Let's jump right in. Welcome to this explainer. Today, we're diving into something that literally sounds like it was pulled straight out of a sci-fi novel, but it is rapidly becoming our actual reality. We're talking about quantum computing. We're looking at a massive, fundamental shift in how we process information, one that basically rewrites the rules of physics to solve problems that are currently impossible for humanity. Just to give you an idea of the sheer scale we're talking about here, there's a staggering quote directly from Google's recent research, a calculation that takes their latest quantum setup under 5 minutes to complete. Well, that would take the absolute fastest, most advanced classical supercomputer on Earth 10 to the 25th power years. That's a 1 followed by 25 zeros. That is literally a time frame exponentially longer than the entire age of the universe. It's a completely mind-blowing gap. And to figure out how that's even possible, we actually have to zoom way, way in, down to the incredibly small. Section 1. Quantum mechanics in movies. You might not even realize it, but the popcorn blockbusters you've been watching lately, they're actually rooted in the exact same science that powers quantum computers. To really grasp this, we first have to ask an incredibly basic question. Why can't we see atoms? Everything around us, every single material is made of atoms. You're literally looking at atoms right now, but we can't individually see or feel them because they operate on a scale that completely defies our everyday logic. So just how small are we actually talking here? Well, you could line up about 100 million atoms on a single fingernail, but honestly, it gets weirder. If you were to scale an atom up to the size of the massive city of Seoul, its nucleus would only be the size of a single basketball sitting right in the middle of downtown. And the rest of it? Almost entirely empty space. This is exactly the concept that the movie Ant-Man plays with when he shrinks and grows by manipulating that empty space. Though, okay, in real quantum mechanics, you can't actually compress that space like that. And that brings us to another film, the Oscar-winning Everything Everywhere All at Once. In the movie, you've got characters jumping between parallel universes experiencing multiple realities simultaneously. And you know what? This brilliantly illustrates our core scientific concept for today, superposition. In the quantum realm, things can literally happen everywhere, all at once. Section 2. Superposition. Coexistence of 0 and 1. So let's step out of movie magic and directly into the heart of actual quantum science. Think about flipping a coin. When you toss it, you firmly expect it's going to land on either heads or tails, right? There's absolutely no in between. But superposition in quantum mechanics is kind of like a spinning coin in midair. While it's spinning, it is effectively both heads and tails at the exact same time. It's not one or the other. It's a simultaneous coexistence of both states until it's finally observed. Now, let's look at how this builds a completely new type of computer. Classical computers, the ones we use every single day, use bits. They rely on electricity, right? So current flows, which is a 1, or it stops, which is a 0. It's purely digital. But a quantum computer uses what's called a qubit. And because of superposition, a qubit can be 0 and 1 at the exact same time. It holds both possibilities at once. So the crucial question here is, what does this actually do for us? Well, imagine searching for a specific name through a stack of 100 documents. A classical computer essentially has to pick up document 1, check it, put it down. Then document 2, check it, put it down. A quantum computer, utilizing superposition, effectively looks at all 100 documents simultaneously. It sees the entire stack in one go and instantly finds the match. And the real magic here is that the power of this scales exponentially. If you have just 50 qubits, you aren't just looking at 50 things. Because each qubit holds multiple states, 50 qubits represent 2 to the 50th power. That is over 1.12 quadrillion possibilities, all coexisting and being processed at the exact same moment. It's truly a game changer. Section 3. The collapsing encryption system. Now, if you have a machine that can compute a quadrillion possibilities all at once, our entire global digital security suddenly faces a massive existential threat. Almost all our secure data right now, from your online banking to Bitcoin, relies on the RSA encryption system. And it basically works on a super simple mathematical premise. It's incredibly easy for a computer to multiply 2 giant prime numbers together to make an even bigger number. But if I just hand you that final giant number and ask, hey, what 2 primes are multiplied to make this? It is incredibly hard to reverse engineer. Right now, we generally use encryption keys that are about 400 digits long. If you were to take the absolute fastest, most powerful classical supercomputer on Earth and ask it to guess the 2 prime numbers by trying them one by one, it would take roughly 1 billion years. So for all practical purposes, your data is completely, completely safe. But remember that spinning coin we talked about? Because a quantum computer can check vast numbers of possibilities, all at the exact same time, it wouldn't take a billion years. It could theoretically factor that massive number almost instantly. If a fully functional quantum computer actually comes online, the RSA encryption that is protecting everything we send safely over the internet, it could literally become useless overnight. Section 4. Fatal Flaw. Quantum Errors. Okay, so should we all start panicking? Well, not quite yet. Before quantum computers can break the internet, they have to overcome some massive, almost seemingly impossible physical hurdles. The biggest problem by far is that qubits are unbelievably fragile. Remember, superposition relies on that coin constantly spinning. But the very moment you actually measure or look at a qubit to see its data, the superposition instantly breaks. It just crashes down to a regular 0 or 1. And worse, even ambient air, tiny radio waves, or just a slight bit of heat can destroy the quantum state. That's exactly why these machines have to be kept at near absolute zero, around minus 273 degrees Celsius. And this creates a massive paradox for scientists. Just like everyday data zipping over the internet, quantum data gets corrupted and needs error correction. But how on earth do you check a qubit for an error if merely looking at it destroys the very quantum state that makes it powerful in the first place? Well, back in 1995, scientists proposed a brilliant theoretical workaround for this, called quantum error correction. It's kind of similar to how the final digit of your resident ID number verifies that the rest of the numbers are valid without revealing them. In the quantum world, instead of sending just one bit of data, you send redundancy, like a 111. If some interference changes it to, say, a 101, the system uses a majority rule to deduce the correct data. And it does all this without ever directly measuring and therefore breaking that delicate core quantum state. And this brilliantly illustrates why recent news in the tech world is so incredibly exciting. Google recently unveiled their 105-qubit Willow chip. When they tested error correction by scaling up grids of qubits, going from 3x3 to 5x5 to 7x7 grids, something amazing happened. Historically, adding more qubits just meant more noise and way more errors. But with Willow, as the grid got larger, the error rate actually dropped. They proved that this impossible workaround actually functions in reality. But just to ground the hype for a second, we are still a really long way off from breaking global encryption. Experts estimate that because qubits are just so incredibly error-prone, you might need up to 100,000 physical qubits working together just to create one perfectly stable, error-free, logical qubit. So right now we're celebrating reaching 105. We still have a massive mountain left to climb. Section 5. 100 years toward the impossible. I think it's important to zoom out and look at the historical trajectory of this unbelievable science, just to understand where we might be heading next. Because this isn't some new fad. The foundations were laid nearly a century ago. If you trace the timeline, it all started back at the famous 1927 Solvay conference, where absolute giants of science like Albert Einstein and Niels Bohr fiercely debated the bizarre rules of quantum mechanics. Fast forward to 1995, and we get the theoretical math for error correction. And today, in 2024, we have physical chips like Google's Willow, bringing those 100-year-old debates to actual life. You know, you'll hear people today say quantum computing is decades away, or maybe that it's impossible to scale. But historically, declaring scientific progress impossible usually ages very poorly. When classical computers first came out, the president of IBM allegedly declared they were just too expensive and complex for the general public. Back in the 19th century, scientists claimed we would never know what the moon was made of simply because we could never go there. And yet here we are, with smartphones in our pockets and footprints on the lunar surface. We are standing on the very edge of an entirely new frontier of human capability. We're building a machine that computes the universe not in binary, but in infinite, simultaneous possibilities. So what you should take away from this explainer is not if these machines will change the world, but rather this: when will the impossible become our new reality? Thanks for exploring this truly fascinating topic with me.